So yesterday we talked about hypothesis or significance tests for one proportion or one sample proportion using the NBA bubble example during COVID. So we kind of talked about hypothesis tests without getting too deep in the math. Okay, we talked about how to set up hypotheses. We talked about how, and we used a dot plot to figure out a probability or a p-value. And if that was less than what we said was our alpha value, then it's unusual. And then we have evidence for the alternative hypothesis. If the p-value was really high, above whatever level we set, well, then that's not unusual. Therefore, we can't accept the alternative. We just don't reject the original, or don't reject the null. So we're going to get a little bit more mathy. And then just like we did with confidence intervals, we kind of did it sort of the long way, and then showed you how you can use that four-step process and the graphing calculator to do all those little calculations for you. Okay? We're going to do much the same with this. So again, just to remind you, okay, the situation was we were trying to see if during this bubble, home court teams had an advantage. And so the league randomly assigned, should be randomly assigned each team to be the home team in its 4 of its remaining 8 games, obviously away in its other 4 games. And it turned out that of the 88 games played, the home teams won 49 times, or which worked out to about 56%. Okay, and the whole question we wanted to answer, was there convincing evidence that there was home court? And we saw that, well, because it was 56% is greater than 50%, which we figure is the cutoff for home court or no court advantage, we said it might, but that could have just happened because of chance. Okay. So what should you do when you see the phrase convincing statistical evidence? We talked about this yesterday. It means you should perform perform the hypothesis test. Perform a hypothesis or significance test. And as soon as you see that, that's when we set up the null and alternative hypothesis, and then do our calculations from there. Find the p-value and see if it's below or above what we've set as the alpha value. So remember what we said in this situation, in a world where we assume, so in a world where we assume there is no home court advantage, there is no home advantage, that's the assumption, that's the null hypothesis. Okay? What are the chances the home team wins 50? What are the chances? The home team wins, and remember we're getting this, I'm going to write it like this, just to remind you where this 56% is coming from. Remember, 49 out of 88 teams, or sorry, 49 home wins out of 88 games, or 56%. And then remember how we set it up. We said, okay, mathematically, we have the null hypothesis, And we're going to use the population proportion, right? Not the sample proportion. The sample proportion helps us establish whether this claim or whether there is statistical evidence for this claim. So we said that the proportion, no home court advantage, which means the proportion should be 50%. Not higher, not lower, half and half. That's no advantage. But we were trying to test when it was actually bigger than 50%. And then you have to put this along with it. P is the true proportion of home gains won. You have to identify what P exactly means. And we're always going to use the word true because we're using the population proportion, which is true or actual proportion. So we set that up, and then last class we saw that we used a dot plot where the season was simulated 100 times. And we found that we got 56% or higher 14 out of those 100 times. Okay, so the p-value we got was, or the probability, I'll write that in a second. 14 out of 100, 14%. And what's the interpretation? In a world, again, in a world where there is no home advantage, we got a probability of the home team winning 56%. (14% of the time. It happened 14%, 14 out of 100 simulations. Now, 100 seasons won't account for all possible situations that happen. It will be close enough to see that it follows a normal pattern, and therefore we can do normal calculations. But to make it more precise, we would actually go beyond the 100 seasons and do many more in a simulation. And how do we calculate it? Well, as long as conditions are met, which we'll talk about a little bit later on, we can say the sample distribution is normal. We can say the average of all the proportions we got will work out to the null proportion, 0.5. That's the only one we have to look at. And then the standard deviation will be the square root of the null proportion times 1 minus the null proportion divided by the sample size. Okay, so notice that's a little bit different. Remember, with confidence intervals, we used p hat. Okay, in this one, we use the null proportion. So in our specific one here, and I'm just going to write here, this is the assumed P under the null hypothesis. That's why we use it. So that means this is going to be 0.5. And this is going to be the square root of 0.5 times 1 minus 0.5 divided by the sample size, which is 88, which gives us a standard deviation of approximately 0.053, which kind of tells us something right there that standard deviation is pretty small. So that means that our observed, the 56% we got perhaps is not that far off from what's under the null hypothesis. But we want to calculate how many standard deviations that is away. And how do we calculate how many standard deviations away? Well, if you remember back to Unit 2, we calculate a Z-score, which was defined as how many standard deviations a value was away from the mean. And we use this formula, and it's actually on the next page. It's the data value minus the mean of the data divided by the standard deviation. That's what we did in Unit 2. We apply that same reasoning to this one, except we don't call it a Z-score this time, we just call it a Z-statistic, because that's technically what we're calculating. And it's going to be the data value we got, the statistic, minus the mean, which is the proportion under the null hypothesis, okay? Which is the null value parameter. That's the mean, because we said that up here, right? Divided by the standard deviation, and we've got those values. What did we get in our statistic? 0.56. What was the null value parameter? What did we assume to be? 0.5. Divided by the standard deviation, which we calculated. 0.053. And that means that's going to be approximately 1.08 standard deviations, which is not a lot. Remember when we said approximately 68% fall within one standard deviation? This is almost there. This is almost within the 68%, which is not unusual at all. So that's kind of we're not quite finished yet, because we actually have to figure out the probability now that we've got this. But here I just that's kind of a recap of what I did on the previous page. So you can see here the Z statistic is how many standard deviations a statistic is above or below the parameter value, or the mean, which is the parameter value in this case. And the larger that number is, that's test statistic, that Z statistic, like I said, the more unusual it's going to be. The smaller it is, that means the closer it is to the null. which means it's not unusual. But as the standard deviations increase, the further and further it gets away, then it's becoming more and more unusual because it's really far away from what we would expect. Okay. Question is how far away, or what's the probability, which means we got to find the area. Remember, how do we find the area? Well, we're going to go back to this normal distribution where this is one standard deviation from here. This is two standard deviations. This is three standard deviations, which means this value must be what? 0. And then these must be -1, -2, -3. So the mean has to be 0, and the standard deviation is 1. And remember what I want to find. We had 1.08 about there. This is going to be the probability of greater than that. That's what I want to find. That's going to give me my p-value, or probability. And how do we find it? Well, we're finding an area of a normal distribution, which means normal CDF. What's the lower boundary? 1.08. What's the upper? 1,000 sounds good. The mean is 0, and the standard deviation is 1. And we should get, remember when we did the dot plot, we got 14%? We should get somewhere in that vicinity, but this will be a more accurate measure. Okay, because we did more simulations. We represented it better. So if we do this, we should get, what do I have here? Oh no, actually I think it works out to the same thing. I thought it was different. I thought it was a little different. I didn't think it was that close. Let me just double check that I did that right. Distribution, we have 1.08 up to 1,000, 0, 1. Oh no, that's pretty close to 14%. Okay, so it pretty much matches what we did from our dot plot. So you can see that's kind of the long way to do it, right? So you'd have to set up your null and alternative hypotheses, okay? Yeah.
If the two numbers were a bit different, is this one more?
Yes, the one that we just did. Yeah, using this instead of this is more accurate. Yeah. So remember, the long way would have been, just like we did with confidence intervals, we had to calculate all this stuff. And then for confidence intervals, we had to figure out the critical value. For here, we had to figure out the Z statistic. Then we had to use the normal distribution to find the likelihood. Okay, whereas with confidence intervals, we actually were having to find the area like 95% or 90% or 99%. We found those boundaries. Here we're kind of going in reverse. We're finding the probability of that area. But there is a quicker way we can do it. Where, like I said, all that stuff, all that normal, the mean of the sampling distribution is equal to the null parameter, And the standard deviation of the sampling distribution is the square root of, you know what I'm talking about? And then having to do the Z statistic and then having to do normal CDF. This thing's going to do it all for you, and it's going to spit out the p-value. Okay? There's just certain pieces of information you have to enter. So let's look at the 4-step process, how you would do it. So same question. This is what it would look like. Okay? And notice this tells me right here, do a hypothesis test. That means set up the HOHA. And notice it tells us the significance level. We need to know that significance level when we get the p-value. Because if it's above the p-value above it, okay, we don't reject HO. And if it's below it, we do reject HO. So same. Remember just what I did in the previous. So we're going to go like this. This is where we're going to put our hypotheses and what P represents. So we're going to have this. Remember the status quo was no home court advantage, or the null hypothesis. We were trying to prove if there was home court advantage, which means it has to be greater. And then we had to define what P was. True proportion of home team wins, you could say. Now here, if you want to remind yourself what the alpha level is, the significance level is, you don't have to write this, but you could. It's not really that necessary. The plan phase is to say, okay, what are we going to do? And can we do it? As in, are the conditions met? Okay, so the plan phase, I'll put up here, next page. We are going to, we're not going to create a confidence interval or calculate a confidence interval. We are conducting or performing, either word. We are conducting a one sample Z test. Remember, with confidence intervals, we were creating or we were calculating a one sample Z interval. Here we are conducting a one sample Z test, because with proportions we use the letter Z for certain calculations. Okay? If conditions are met. So random, 10%, and this is actually going to be an interesting one this time. Large counts. Does it say anywhere in the question that there was random selection or assignment? Well, it doesn't say at this question, but if you look at the beginning of the lesson, after it says home court advantage in bold, it says the league randomly assigned. So teams were randomly assigned, either to be home or away. So that's okay. That meets our random condition, which means that we can say that the average of the sampling distribution is equal to the null value, 0.5. The 10%, this is kind of an exception. Notice, or perhaps you didn't notice. When we did confidence intervals and we tested the conditions, it was always about, were they randomly selected, right? Were the objects randomly selected? Were the people randomly selected? What's different about this? They're not randomly selected. They're randomly assigned to two groups. What's that? When we do that, when we randomly assign people or objects to two groups, don't overthink. And then we test them. What do we call that? An experiment. It's an experiment. So, because it's an experiment, independence is assumed. So, whenever there's an experiment, we don't need to test this. So you can just say, don't need, or not test, check. And the reason is because it's an experiment. Independence is assumed. Because remember, 10% is the independence condition. Most of the time, you're going to have to check whether your sample size is 10% of the, or less than 10% of the population. But in this case, you don't have to, because it's an experiment. The large counts you have to. So you got to take your sample size times the null value, and that has to be greater than or equal to 10. And then you got to take your sample size times 1 minus your null value, and that also has to be greater than or equal to 10. So sample size was 88, null value was 0.5. 44, that's good. $88 times 1 minus 0.5, which is the same thing. 44. We're good. We can continue. Okay. Now, here's where we use our graphing calculator. And we are going to this a one proportion Z test. It's under number 5, under the tests. So this is the do section. We're going to do a one prop Z test. And when you highlight that, you'll see what you have to enter. It's slightly different than when we do confidence intervals. So tests, go down to number 5, one prop Z test. It asks for the null value. P0, which we've established is 0.5, no home court advantage. X is actually what happened in our sample. Okay, and what happened in our sample? The home team won 49, right? The sample size was 88. And the last thing, the prop, or the proportion, is our alternative not equal to 0, not equal to P0, less than P0, or greater than. Which one is it? Which one was the alternative? Not equal, less than, or greater than? Greater than. So that's the one you highlight. That's the one you highlight. So making sure that's highlighted. So 0.5, 49, 88. That's highlighted, calculated. Notice, look for P, not P hat, just P. That's your P value. 0.143, and we saw before it was around 14%. What's that? What's the color? Let's wrap this up. So, what you want to do
is you want to look for P, because that represents the P value. And it worked out to, what was it, 0.143?
Yes.
Around there, if I go to 3 decimal places. So now the conclude is to compare your P value against your alpha value. So because 0.143, the P value, is greater than our alpha value, which remember was 0.05.
That means our result is not unusual. That means that we don't have evidence for the alternative, which means we're at the null. Remember, we never accept the null, we just don't reject it.
So we fail to reject HO. We don't have convincing evidence there was a home court advantage. We don't have convincing evidence there was, and I'll just put a home advantage.
And that's what it should look like when you conclude a hypothesis or significance test. Now, most of the ones we've been doing to this point, like when we set up our hypotheses, HO is always going to be, when we do proportions, P equals whatever the status quo is. It's always P equals. The alternative changes. It's not going to be equals. It's going to be greater than, it's going to be less than, or it's going to be not equal to, depending on how the question is phrased. So in this one, we were looking for evidence of a home court advantage, which means greater than 0.5. Perhaps if it said we were looking for an away court advantage, then we'd be looking at less than 0.5. If the question said to you, is there no difference in home or away court advantage? That's not equals. It's not telling you greater. It's not telling you less. It's telling you it just isn't the same. So here's an example where we use not equal, and that's called two-sided test when you are testing an alternative in both directions. Greater than or less than. That's what, and then we use this. So the question with the NBA bubble would be phrased, is there convincing statistical evidence that either home or away teams had an advantage? Another way it could say, is there convincing statistical evidence that there's no difference in home or away team advantage? So let's just do it really quickly. The state we're just going to write this out. We're not going to do the conditions. We're going to assume that they're met. So the state, remember, HO P is equal to 0.5. This time the alternative is P not equal, where P true proportion of home games won. True proportion plan conduct
one sample t-test or one sample z-test, pardon me, t-test is something else. One sample z-test. Let's assume the conditions are met because we met them last time. This time we're going to do that crop Z in test again. One crop Z test. Everything's going to be the same. What's the first thing? This is 0.5, 49, and it's 88. At this time, the proportion not equal.
So when you do that one, change, only thing you have to change on your test is from greater than P0 to not equal to P0, and then you calculate it. Notice the p-value, boy, it's really 0.286, almost 29% probability. Okay.
So the conclusion would be because our p-value is greater than our alpha value, our alpha level.
It's not unusual. Okay, which means there's no evidence for the alternative, which means we don't reject the null.
And if we don't reject a null, remember the language I said, we fail to reject. HO. We don't have convincing evidence.
How I phrase this to make sure I say this funny.
We don't have any evidence either home or away has an advantage. Because we changed the questions slightly.
Okay, so that is hypothesis tests. One thing left to do, I can start recording here, which we'll do tomorrow,